we have this concept, you should have this idea of what inertia is. All right, now I'll restate it again. Inertia is an ability of some objects to resist an acceleration. All right, that's the simplest way that it can be put is the ability of an object to resist an acceleration. In the translational world, mass and inertia are basically equivalent. All right, the mass of an object tells you how strong of a force is required to cause that object to accelerate. When we're talking about rotational motion, though, which we're talking about now, life gets a little bit more complicated. And as we found out yesterday, the way that it gets more complicated is we have to add in this dependence on the radius of the object. Somehow we have to account for the radius of an object. But in essence, when we're calculating the moment of inertia, what I want you to keep in mind is if something has a big I, it has a big moment of inertia, that means basically that it's hard to get spinning. And also hard to stop spinning. If it has a small moment of inertia, all that means is that it's easy to get spinning. In much the same way that if you have an object with this large mass, it's hard to get that mass moving if it's not moving. And if you have an object with a small mass, it's easy to get it moving. All right? So today we're going to take a few minutes and figure out how to calculate the moment of inertia for different objects. Now I want to break this discussion up in two sections. The first thing that we're going to talk about is how to calculate the moment of inertia for what I call discrete objects. All right, so we're gonna start off with discrete objects. And what I mean by discrete objects are objects that we sort of treat as like point objects. In other words, imagine that I've got some sort of a strangely shaped wheel, and that wheel has a few different spokes, and on the end of each of these spokes, there is some mass. All right? We're just doing this in the general sense, so the shape of the wheel doesn't really matter. What does matter is that each of these masses can be different. So this is mass 1, this is mass 2, this is mass 3, this is mass 4. And that each of these masses, this is spinning around the axis of rotation that's right in the center here of this little dot. So imagine that this thing is spinning like this. All right? And what does matter is that each of these masses could be at a different distance from that axis of rotation. So we could call this like R1, this is R2, this is R3, this is R4. All right? So these are sort of what I consider to be discrete masses. Okay, yeah, it's a block or whatever it is, but it's some object that basically we could just sort of treat as a point that's orbiting some axis of rotation at some distance away. All right, we don't necessarily care how thick this mass is. We'll just treat it as a point, and it's rotating around some axis that's much further away than the diameter of the object itself. Okay? So for this case, we can calculate the moment of inertia just like we talked about yesterday at the end of class. All right? Calculating the moment of inertia is relatively straightforward. We calculate the contribution to the moment of inertia from each mass. So in other words, what we did yesterday is we discovered that this I thing for a particular discrete mass is something like m1 times r1 squared. And we add up the m1 r1 squareds for each individual mass. So m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. Or if I wanted to write this in a nice compact manner, I'd simply say that the moment of inertia is the sum over something like I, where I is the ith mass of mi times ri squared. All right? We talked about this yesterday. It basically came from trying to write an equation for kinetic energy of a rotating object in a nice compact form. Right? This is the moment of inertia that we get for a set of discrete objects that are orbiting around some common axis of rotation. Right? Like you said yesterday, like I said at the start of class, it depends, okay, yes, on the mass, because mass, we've always thinking about that as inertia, but also on the radius. And not just the radius, but the radius squared. So the radius is extremely important. Right? So no big deal there. The hardest part about doing this calculation is actually identifying the fact that you're dealing with what we would call a discrete object. For example, let's say I wanted to calculate the kinetic energy of the Earth as it orbits around the sun. All right, we could do that calculation. The Earth is orbiting around the sun with some angular speed, some omega. In order to get the kinetic energy, I need to know the moment of inertia of the Earth orbiting around the sun. So I need to know the mass of the Earth. I need to know the orbital distance from the Earth to the sun. Right? I can calculate the moment of inertia using those two values, and I can get the kinetic energy. All right? The Earth would be treated as a discrete object there. Why? Because the radius of the Earth is much, much, much smaller than the distance from the Earth to the sun, distance from the Earth to the axis of rotation. Okay? In general, that's what you're looking for. Now, maybe it'll be a little bit more obvious when we talk about the second class of objects. What I call continuous objects. All right, when I say a continuous object, what I really mean is an object that sort of, just itself is rotating. It's not necessarily rotating about some axis of rotation far away. It's just, it's just rotating like a wheel. So maybe the simplest thing to look at is just a disk, like a solid disk. And this thing is just rotating like so. Maybe with some angular speed omega. You could also imagine a cylindrical rod. Which is rotating maybe about the axis right down the middle of the cylinder. Right? Actually, you could take that rod and you could look at it in a couple different ways. You could actually, instead of allowing that rod to rotate along its axis, you could say, well, actually, what it's doing is it's rotating about some axis perpendicular to the rod. All right, these are examples of what I mean by continuous objects. In other words, you can't really define like some point on this mass that's at some radius, as in the radius in our calculation, mr squared, from the axis of rotation. Why? Because, well, part of the mass is, is here, and it's at some radius from the axis of rotation, and then there's some part of the mass out here that's at a different radius from the axis of rotation. So life becomes a little bit more tricky. Right? If you think back to your calculus class, you may have seen something like this before. In order to calculate the moment of inertia, we have to do a little bit of integrating. All right? And the thing that we're integrating over is a little bit confusing. It's not some coordinate system. It's actually some mass. We're actually integrating over some infinitesimally small chunk of mass that is sitting at some distance r from the axis of rotation. All right, and if you look at this equation, it looks very similar to the one that we had just up above a second ago. There is this mr squared term in here. It's just m is some like really, really small chunk. In other words, what are we really doing? We're breaking up this continuous mass, this continuous object, into a whole bunch of little objects that we call dm. And then we're just adding up the contributions from all those individual dm's times their radii squared to get the moment of inertia. Right? So really we're doing the same thing, we're just kind of invoking a little bit of tricky, more advanced math. Right? So the real question is, well, did you guys ever learn how to integrate over dm? What does that even mean? I would dare say this is one of the the more difficult parts of the math in this course, is trying to understand what integrating over dm really means. All right, pictorially we have it written right here, right? We're breaking up our mass into a bunch of little chunks, but usually when we do integrals, real integrals in physics class or real derivatives in physics class, we're integrating over like some coordinate system, right? We're integrating over like x or y or z, or maybe all three. So this is a little bit strange. So in order to solve this problem, what we have to do is we have to be able to change the thing that we're integrating over into something that we could actually, integrate over. I mean, right? Because what we really want to do is we want to say, okay, well, this mass extends from some radius of 0 out to some radius of whatever this is. Call it, I don't know, let me call it capital R, the radius of the rod. So really what I feel like I want to integrate over is the radius. I want to be going from, an r equals 0. The limits of my integral, in other words, would be from 0 to capital R. So I need to sort of write dm in those types of terms, in terms of my coordinate system. And we can do that. We can do that by exploiting a property of mass known as the density. So what I can do then is I can realize that, well, mass is related to an object's density, all right, times the object's volume. Or in other words, what is density? Mass density is just the mass of the object divided by its volume. So density, where rho is density, and it has units. The units of rho are kilograms per meter cubed. So if I sort of realize that mass is related to density times the volume, well, then I can rewrite dm in terms of some infinitesimally small volume. So what I really have here is I have something like rho, which is a constant, right? This object, we'll assume at least for now that this object has a constant density. So rho times dv times r squared. All right, and now life is a little bit better because, well, dv is, that's a volume. That has to do with my coordinate system, and I'm perfectly fine with integrating over my coordinate system. So let's do that then for an example involving a real calculation for a moment of inertia. All right, so we're gonna make this a tiny bit more complicated. We're gonna come up with an object. This is going to be sort of like the spinny thing we talked about yesterday. So just imagine that you're kind of chilling out in the spinny thing, and it's attached to this big old rod, which is fixed at the middle. And then on the other side, there's another little box with somebody else chilling out inside. Okay, so let's imagine then this thing is rotating about this axis of rotation. It's going in and out of the board, so it's actually rotating. Let's say it's coming out of the board here and going into the board on that side over there. So really, on this side, the velocity is into the board. On this side, the velocity is out of the board. All right, so the guy on the left is coming towards you. And of course, we know that we need to define some radius. So the boxes are at a distance r from the axis of rotation. All right? In our previous sort of calculation yesterday, when we did the spinny thing, we sort of inherently assumed that this big old bar was massless, because we didn't account for the moment of inertia due to this cylinder. We just sort of treated the moment of inertia due to the boxes on the ends, and then we just added them up in a generic manner. But today we're going to actually account for the fact that, hey, this thing probably isn't massless. It probably contributes to the total moment of inertia. Therefore, it should be accounted when we're trying to do things like solve for the kinetic energy of the system. So really what we have here is we sort of have three different objects. We have the box on the left with the person. We have the continuous object in the middle, the continuous cylinder, and then we have the box on the right. So if I want to get the total moment of inertia of this system, thereby enabling me to calculate kinetic energy, something like that, I just have to simply add together the individual moments of inertia from each of those three objects. All right, fair enough. I look at this picture and I say, well, the boxes themselves, they're not terribly large compared to the radius of the system, compared to the axis they're rotating around, the distance to the axis they're rotating around. The radii are small, so I would say that objects 1 and 2 are discrete. And I would treat them, when I'm calculating the moment of inertia, as discrete objects. So when I say objects 1 and 2, what I really mean is objects 1 and 3. All right, so I could already start to simplify, or I guess expand my total moment of inertia calculation with that in mind. So I'd say something like, all right, well, mass of 1 times r squared, that's the moment of inertia for this guy, for the guy on the left. I don't know what the moment of inertia for I2 is yet. That's a continuous object. For object 3, it's got to be mass of 3 times r squared, because the radius, the distance to that guy is the same. All right, so the question becomes then, well, what about I2? What is I2? So this is the aforementioned tricky continuous object. So let's break this up into, let's take a look at this big old arm, and we'll sort of we'll zoom in a bit. And we'll just look at part of the arm. All right, so I'm just going to look at the left half of the arm. Keep in mind that this arm goes out to the right. So it's orbiting around this center of mass, and we're doing like a top-down view, and I'm going to say that it's rotating like so. An angular speed of omega around the center of mass. So we've gone from this picture up here where the object is rotating, in and out of the paper. Now I'm looking top-down from a top side view of the actual cylinder. So it's rotating around the center of mass like that. So if I define my coordinate system such that, the x direction is something like that, right? I need to come up with a solution for the moment of inertia based on this coordinate x. So what I'm thinking I want to do is I want to break this guy up into chunks. All right, so this is some chunk of mass dm, and this dm is sitting at some distance x away, right? Because my coordinate system is x, so I'm going to call it x instead of r now. And I can write down the contribution of this mass, dm, to my total moment of inertia. In other words, I'm going to calculate the infinitesimally small component of the moment of inertia for mass number 2, which I'll call di. And I know that's got to be equal to dm times r squared, right? That tiny little chunk of mass, well, that's really just become a discrete object. And if I want to find the total moment of inertia, I2, I just need to add up the contributions from all these individual dm's as I go up and down the length of the arm. All right, so how can I figure that one out? What is dm in this case? So like I said before, we can relate dm to the density. In this case, I just have a one-dimensional object. I'm not really worried about, this thing is really thin. It's not very deep. I'm just worried about a single dimension. So I need to calculate the linear density of this object. Now remember, this has total length r. I'm sorry, I wrote r here. This should be an x, right? Because I'm only going from the axis of rotation to dm, so I called that x, not r. The total length of the whole arm is r. All right, so the dm, the infinitesimally small mass, I can write that as the mass density, which is the total mass of the object, divided by the length of the object. So this is a linear mass density, because I'm assuming it's a one-dimensional object. And then I multiply that dx. So this is just the density. This is like rho in a 1D sense. And then I'm multiplying that by dx. So just some infinitesimally small distance to get how massive this little chunk is. Right? In other words, this guy right here has the dimension dx. That's how wide it is. That's how thick it is. And if I want to find out how much that weighs, I have to take its thickness and multiply it by the mass density of the object. That's exactly what I've done here. So what this allows me to do then is to actually put my moment of inertia calculation in terms of a variable that I could actually integrate over, dx. So now I get di is equal to m over r x squared dx. So what I'm allowed to do now is, since I have something that I can actually integrate over, now I just want to add up the contributions from every little chunk of mass. In other words, I do want to do the integral. So what I'm going to get is that I2 is equal to the integral of m over r times x squared times dx. And I'm integrating over some limit, some bound. So I'm integrating from the axis of rotation where x is 0 all the way down to the other end of the mass, to r. All right. Now remember, r is a constant, so this m over r thing, that just comes right out of my integral, because r is just the radius of the arm, of the cylinder. So I can pull that out. So all I'm integrating is x squared dx over the limit 0 to r. And that's not too terribly bad. I get a 1/3 m over r, and then this goes to an x cubed. And then I apply that from 0 to r. All right. The 0 goes away. The 0 doesn't do anything. It causes the whole term to go to 0. So what I'm going to get is 1/3 m over r times r cubed, which is really just 1/3 m r squared. So that's the moment of inertia due to the cylinder, due to the left half of the cylinder. I only did it for half of the cylinder. So this is really not just I2. This is I2 just left. All right, so remember, I cut off the right half. There's this whole other half. But it's the same exact thing. It's just a mirror image. So really, I just get another factor of 2 there. So if I want to figure out the moment of inertia due to the cylindrical arm, it's twice this guy, or 2/3 mr squared.